Hello, Amba. We're going to talk today about a forecasting method called exponential smoothing or exponentially weighted moving average. But first, let's orient ourselves to the big picture context. I promised you that you would see this slide a lot. Think of it as a slide about what wastes managers' time. Let me ask you to think about how much of your time, your boss's boss's time, get consumed by number one, dealing with problems that resulted from variation from the way that you had planned things. Number two, dealing with a dollar's worth of headaches created by somebody somewhere else in the organization that was trying to save a dime's worth of cost. And number three, refereeing conflicts between different people having different goals in their job. We are going to eventually clarify and strengthen our thinking on these issues by applying the science of supply chains. In that science, if you specify certain inputs to a link in a supply chain, you can predict the performance of that link and ultimately predict the performance of the entire supply chain. One of the inputs is a representation of customer demand. And that's the piece we're going to focus on today, characterizing customer demand using a model called exponential smoothing and also called exponentially weighted moving average. First, let's review. A time series is a sequence of numbers that represent something that is happening over time. The z's are the numbers that we are observing, and the subscript t represents the time. T could represent the day, the week, or even the year. And capital N represents the number of periods in which we have made observations. Here's an example. Here, Z represents weekly sales, T is the week, and N is 20. There are 20 weeks of observations. And if you look at the graph, you can see that the sales vary quite a bit from week to week, but there's a little bit of an upward trend over time. Let's review our notation. The hat on the T means that it's a forecast rather than an observation. The T tells us the week in which the forecast was made. The L in parentheses tells us whether we are forecasting for the next week, which would be L equal 1, 2 weeks, which would be L equal 2, and so forth. For example, Z hat sub 15 means that we're making a forecast in week 15. L equals 5 means that we're forecasting 5 weeks into the future to forecast what the demand for week number 20 will be. We're going to introduce our new forecasting rule called exponential smoothing. Let's assume that last week we had a forecast of what was to happen this week. We will create a new forecast by adjusting the old one. If the old forecast was too low, we will adjust it upward, and if it was too high, we will adjust it downward. Now, the way we will do this adjustment is by taking a weighted average between this week's observation and last week's forecast. Here's the math. In week 1, we set our forecast to whatever we observe. So in week 1, the forecast of all future weeks is just whatever demand we observed in that first week. Then each week after that, we adjust the forecast by using this very messy looking formula shown here. The only thing I want you to remember about the formula is that it uses some fraction which we denote by the Greek letter lambda. And lambda is the weight that we're going to place on the current week's observation. And 1 minus lambda is the weight that we will place on the old forecast. That weighted average is our new forecast. We get started by making a forecast in week 1. The forecast that we make in week 1 is just the observation 9,900. Then week 2 rolls around and we observe a demand of 9,890. We multiply the 9,890 by 0.27. We multiply the old forecast by 1 minus 0.27, and we add those numbers together, and we get a new forecast of 98.97. Note that the week 1 forecast was too high by 10, so we lowered it by 27%, or 0.27 of that amount. Week 3 comes. The actual demand was 10,137. I multiply that number by 0.27. I multiply the week 2 forecast by 1 minus 0.27, and I add those two numbers together to get the week 3 forecast, and that is a forecast of weeks 4, 5, 6, and so forth. This table shows the forecast that we've updated week by week, and the chart shows the observations plotted versus the forecast that was made in the previous week. Note that the forecast trend upward following the data, but the forecast doesn't jump around nearly as much as the individual data points do. Now let's revisit the errors. We did this before in RP1 when we did the random walk model, but at my age I forget things, so we're going to do it again. To get the error for period 1, you remember what the forecast was that you made in period 1, and then when period 2 rolls around, you take what you observe and subtract the forecast. I'll say that again. The error for the first week is what happened in the second week minus the forecast that I made in the first week. In this case, I forecasted 9,900. Week 2 rolled around and I observed 98.90. So the difference between that actual and the week 1 forecast is minus 10, and that's my week 1 forecast error. Here we have all 19 errors. We can only compute 19 because the forecast that we made in week 20 will have to wait until week 21 rolls around before we can compute an error. And we follow two conventions in dealing with errors. The first one is that the error is measured as actual minus forecast. In other words, just remember to keep them in alphabetical order. The second convention is we associate the error with the period in which the forecast was made, not the period in which we observed the outcome. So E sub 2, for example, is the error associated with the forecast that we made in week 2 for the outcome in week 3. So it's actual of 3 minus forecast of 2 is the error for week 2. So we want to measure the quality of the forecast in some way. And if you look, you notice about half of the errors are positive and about half of them are negative. So average error doesn't tell us a lot because it's probably going to be pretty close to 0. So what we want to do first is to square all of those errors, and we're going to use that as a measure of the accuracy of the forecast each week, the square of the error that we made. And then what I want to do is to take an average of those squared errors. We add all 19 up and we divide by 19, and this is called the mean squared error, or MSE. And you'll get some kind of big number that really doesn't mean too much to us just by looking at it. Then we take the square root of the mean squared error and that is called the standard error, or SE. In this case, it is 132. That number tells us a lot. Here's the mathematical formula for what we just did. We use the Greek symbol sigma with a subscript e to denote the standard error. That's analogous to the standard deviation of the errors, but it's computed a little differently. And the formula says the way that we compute it is that we take each of those 19 errors and we square them, and then we add them all together. And then we divide by 19 to get the average, and then we take the square root of that average. Like I said, the standard error tells us a lot. The rule of thumb that you want to remember is this one. Almost all of the errors should be between -3 and +3 standard errors. This means that the actual outcomes will be within 3 standard errors of the forecast made in the previous period. And any values that fall outside that predicted range of variation are indications of special causes or events that are not a usual part of the process. This chart shows a plot of the 20 observations of sales. The line in the center shows the forecast that was made in the previous week. The lines at the top and the bottom show the forecast plus or minus 3 standard errors, which is the predicted range of variation around the forecast made in the previous week. This is a chart of the errors, and the lines show the plus and -3 standard errors. For you Six Sigma types, this is analogous to a control chart, and I've actually denoted the limits there, UCL upper control limit and LCL lower control limit. For this particular example, all of the errors fell within this predicted range of variation. And what that tells us is there were no special events that occurred while we were collecting this data. The next question is, how did I know to use lambda of 0.27? I didn't, but it makes sense to say that the smaller the standard error is, the better forecast I have, because the bounds around my forecast will be tighter, or the predicted range of variation will be smaller. So why wouldn't I just pick the value of lambda that makes the standard error as small as possible? Well, that's what I want to do. Now, how do I do that? Well, trial and error would be one method, but actually Excel has a routine called solver, and you can tell solver to take the cell that contains the mean squared error or the standard error, either one, and make it as small as possible by changing the value of the cell that contains lambda, and it will do that for you automatically. How do we interpret lambda? Well, if lambda equals 1, like here on the left, you get the random walk model. That's a big value of lambda. And you're putting all of the weight on the most recent observation. The forecast will adjust quickly to levels in the process, but it will also jump around in response to random fluctuations. Now look at the example on the right. If I use a lambda that is too small, I get a really smooth forecast, but it's too sluggish to track the level of the process. The data is trending upward, but the forecast isn't keeping up. And it's too low all the time. In fact, 17 times out of 19, the forecast was too low. So you can think of lambda that minimizes the standard error as making that trade-off between responsiveness to changes in the level and the ability to filter out random fluctuations and the data. Okay, now that I've kept your head dunk deep in a bucket of math, let's come back up for air. Here is where what we did will fit into our supply chain model. If I can characterize the demand by fitting it to an exponential smoothing model or some other time series model, and I can state a lead time and I can describe the ordering policy, then I can predict the behavior of the inventory and the stream of orders. So I can take a supply chain that looks like the one on the following page. So I can take a supply chain that looks like this and I can predict what the performance of this supply chain will look like, and that performance will correspond to what I'm observing in the supply chain in the real world. And then I can predict what would happen if I were to do this instead.